So we'll take a look now at a couple other instances where we have these electron configurations, and sometimes they don't match up to what we would expect based on the filling order. And again, we can reason through it just based on this whole idea of stability. So let's take a look at a couple of these that happen in the D block. And generally, when we look at the D block, which again is just that big, huge depression here in the middle of the periodic table. So this region, like I said before, we typically, assign this the D block because we're filling in the D electrons. Generally, we refer to the D block element as the transition elements or the transition metals, for instance. However, a lot of times we forget that the last column here in the D block actually isn't classified as transition metals because the way that we define a transition metal is they either have incompletely filled D shells, so transition metals, or transition elements have incompletely filled D shells or readily lose electrons filled D shells. Really, it's the first 9 rows here in the D block that actually can be classified as the transition elements or the transition metals. Now, we do see a couple anomalous instances of electron configurations for those for a couple of those elements, and two of the more common ones that we'll see are chromium, atomic number 24, and then we have copper, atomic number 29. So let's first of all take a look at chromium, uh, atomic number 24. And we'll find it on our periodic table. Okay, so chromium right here is where chromium is. So we have 24 electrons. And again, if we use our noble gas configuration, we go backwards from chromium. Noble gas that came before it is argon. S2 to get me to calcium. Then when we get to the D now, the D block here is numbered 1 less than the S. So the S was 4, the D would be 3, so 3D, and then we go 1, 2, 3, 4. Okay, so chromium, we're thinking based on the rules, should be argon 4D2, I'm sorry, 4S2, 3D4. This is what's expected, okay, but it's not this. And why is it not? Well, if we take a look at these electrons and we would kind of show them in our electron orbital diagram, okay, there's my 4s, the 2 electrons in it, and then my 4d now, I'm sorry, the 3d, remember the d's have 5 equivalent orbitals, 5d orbitals, so 1, 2, 3, 4, 5. This is my 3d sublevels or subshell with the 5 d orbitals. So I have 4 electrons, 1, 2, 3, 4. Okay, so what actually is preferred is instead of having a filled 4s sublevel and a 3D sublevel that is that looks like this, what is preferred in terms of stability is the following. So preferred in terms of stability is instead having an electron configuration that actually now looks like this. We're going to have argon, then we're going to have 4s1, 3d5. So if I were to again now draw these valence electron, the outermost electrons in orbital diagram form, there's my 4s orbital, And then I have my 3Ds. I have five of these. So one, two, three, four, five. So saying forest one, and then 3D, one, two, three, four, five. So what happens now is both the forest and the 3D, these are half filled. Okay, and the reason that that is preferred is that there's a slightly greater stability associated with these subshells that are either completely filled or half filled, right? So greater stability associated with half filled. So this would be D5, in other words, or completely filled, which would be D10, the subshells. And we're going to see something similar in the case of copper as well, right? And you can kind of look at that on your own. But for the chromium case, this is the reason why it's actually argon 4s1 3d5 and not 3d 4s2 3d4, right? And it all comes down now again to stability, right? That's the driving force, that's the underlying theme through a lot of these chemical principles, properties, trends, etc. Okay, so the last thing we're going to do in this section is take a look at how the periodic table is organized in a little bit broader scale. So if you remember now, in the bottom of our periodic table, we have two rows that kind of stick out from the bottom. Sometimes you might see in your periodic tables, you might have lanthanum actually inserted in here like this. And sometimes you'll have actinium also in there like this. So AC, for example, might be in here, and lanthanum might be in there, or they might just be pulled out altogether. This down here is called the F block. Recall these two rows, that's the F block. The first row of the F block is called the lanthanides, and the second row is called the actinides. Okay, named after the first element, actinides. Rewrite that. Named after the first element in each of those rows. Collectively, those two rows in the bottom are called the F block, and they're filling in the F electrons. And the reason why we don't stick them in, and we kind of take them out, is because if we did stick them in, guess what our periodic table would look like? It would be way too extended, way too broad, and it won't be the concise periodic table that we're used to today. Let's take a look at some other ways in which we classify the periodic table. So when it comes to combining, several of these groups, what we find is that we collectively refer to groups 1 and 2, okay, 1A and 2A, in other words, along with groups 3A through sometimes 7A, but sometimes we also include 8A in this. We refer to these as the representative elements or the main group elements. Okay, representative or the main group elements collectively refer to those. Okay, so the main group. When we start looking at periodic trends a little bit later on, we're going to be focusing mostly on the trends in the representative elements, right? So groups 1A, 2A, and then 3A, 4A, 5A, 6A, and 7A, and 8A. So remember, with our numbering of the groups, we're using the A numbering system because that is a little bit more applicable to some of the stuff that we're going to be looking at. So 1A through 8A, those are the main group of the representative elements. Noble gases found in group 8A, remember those have completely filled, I'm sorry, they're called noble gases or the inert gases, meaning they're unreactive. Okay, and the reason for that, the reason that they're unreactive, they don't like to play well with others, is because they have completely filled p subshells, right? So remember now, if you have a completely filled p subshell, that would be p6, right? Whether it's 2p6 or 3p6, 4p6, etc. And this is very stable, okay? Very, very, very stable. Again, stability is an underlying theme through all of these. One exception to this, important exception, is helium. Okay, helium doesn't have a p sublevel. It's only, only has a n equals 1 principal energy level. So helium only has the 1s, but it's 1s2, so it still is completely full. Anyway, so it still follows that completely filled subshell. So it's also very stable. Okay, so that's why it's lumped into that group, the group 8A, the noble gases, because of the same general principle. All right, the transition metals we talked about before, right? So the 10 columns that make up the D block, 9 of them are transition metals. The last column with the zinc, cadmium, mercury, they're not classified as transition metals. We talked about the lanthanides and the actinides that make up the first and second row of the F block, respectively. What we're going to also see is that as we look at each particular group, okay, and again, this now applies to, we're going to focus on the representative elements mostly. The elements that belong to the same group of the representative elements, they have similar electron configurations. So elements in the same group, and again, the group is the column. Similar, we'll say valence electron configurations. So for example, if we look at the group 1A, right, so those are our alkali metals, and group 1A, their electron configurations all end in S1, right? Noble gas, then the valence electrons here are going to be S1s. These are your valence electrons. We can say NS1. They all have one valence electron. Similarly, the group 2A, the alkaline earth metals, similar trend. Okay, they're all end in, their valence electrons end in S2. Again, remember, it's not S squared, it's S2. So the valence electrons here are N, principal energy level S2. They all have two valence electrons. All right, and that is going to be critical when it comes to determining and predicting the reactivity of the elements. And you can maybe see there's a trend here with those first two groups. The group number, group 1A, all have one valence electron. Group 2A have two valence electrons. You can maybe guess group 3A has three. Group 4A has four. If you look at group 7A, has a total of NS2, NP5, 5 plus 2, 7 valence electrons. All right, so we can say then that for the representative elements, the group number is equal to the number of valence electrons. And that is a very important trend. We don't have to think twice about writing a full electron configuration to figure out the number of valence electrons. we can just look at the group number and we'll go all the way back to one that we did previously, which was bromine. If I can find bromine on here, we can locate bromine. There is bromine. Get 35 electrons. We wrote the full electron configuration. We wrote the abbreviated electron configuration. And here you see now for bromine, okay, we have the highest energy level, which is the fourth energy level, have a 4s2, 4p5, add them together, we get 7. Guess which group bromine is in? Bromine is in group 7A. If I zoom in here, there's Br right here. Br is in 7A. Okay, so it makes perfect sense that we can use that trend when it comes to determining the number of valence electrons. And we're going to use that a lot in the subsequent weeks and the subsequent chapters, right? So that, in the case of bromine, is a direct example of the group 7A that we saw down here, right? Noble gas, NS2. In the case of bromine, it was 4s2, 4p5, which gave a total of 7 valence electrons. Remember the group 7, right? These are also called the halogens.